So we saw that variance measures how spread out a random variable is around its expected value. But now we want to ask a more direct probability question. So how likely is it that a random outcome is far from its mean, right? So for example, suppose a bet has positive expected value, so that sounds good, but it does not mean we cannot have a large loss, right? So we may want to ask, what is the probability of a large loss, right? And so these are questions about deviation from the mean, like how far you can be from the mean. And this is where variance can be very useful. But again, variance is just a number. How can we use it to say something more? And this is what, so there are many inequalities for this. One of them is called Chebyshev's inequality, which we're going to see now. And so what does Chebyshev inequality say? So if you have a random variable x with some finite mean, so it has some finite expectation, and some finite variance, and it's common to denote variance by this sigma squared, and then sigma is what's called the standard deviation, right? So it has this variance like this. Then for any t, the probability that x, so think of this as the distance, so this is the difference between x and the mean, absolute. So it's sort of the distance that your random variable will be from the mean. So the probability that this will be at a distance larger than t cannot be more than the variance squared over t squared. And so what this means is that as t grows here, this will grow, and so this becomes smaller and smaller. So it's sort of saying that the probability that you will be far from the mean will become smaller and smaller and smaller as t grows, as this distance grows. And we'll later see examples using this, but for now, I'll show a nice little proof for the discrete case, because it's a nice little simple proof of this fact. So let's do that. So sigma squared, we saw, this is the variance of x. And what is the variance of x? It's the expected value of the distance between x and the mean squared, right? And so if you write out this expected value, so the expected value is the sum over all the x's of x minus your mean, mu here, squared, times the probability that x is equal to this small x, right? So here, to not confuse, let's do the big X with these bars here. So this is the big X random variable, and the small x is the realizations that the random variable can have. Okay. So now what we do is we split this sum into two parts. So you can write this sum as for all the x's such that x minus the mean, that this distance is larger or equal than t, and then you can have this expression here. And you have the other case, so you can sum over all the x's that are such that that happens, plus all the x's, so here, where it's strictly smaller than t. And what we do is we ignore this second part. So the variance is the sum of two things. These are positive, so probabilities are positive, and then square of these real numbers are going to be positive. So that means that everything here is positive, everything here is positive, so this sum is positive. So this means that this is larger or equal than if we ignore one of the terms, right? So this will be larger or equal than just this part over here. Now, notice that this part here, it's all the x's such that x minus mu is larger or equal than t. So that means that this is always larger or equal than t squared. So this will be larger or equal than t squared, summation of the probability x equal to x for all x's such that x minus mu is larger or equal than t. But if you sum over the probabilities that this event happens, so you're just taking for every x the sum of the probability that for that x for this event, this is just the probability of the event. So this is equal to t squared probability of x minus mu, the thing we wrote there, being larger or equal than t. And so now we have that sigma squared is larger or equal than this part. So if you divide by t squared, you get that this is less or equal than sigma squared divided by that. So that's just going to be exactly what we want. So the probability is just divided by t squared. You'll get probability that x minus mu, so here's the random variable, x minus mu is larger or equal than t, is going to be less or equal than sigma squared over t squared, which is exactly what we wanted to prove.